Evening, folks. So let's have a little think about sine waves and frequencies and adding sine waves together. Yeah, and just stripping sound all the way back to what it fundamentally is, I guess. Okay, so here's some MIDI. I need to get myself a nice little FM8. There it is. And this is just running like new sound. There's no preset loaded. There's just this one oscillator going to the output at a ratio of 1, which means it's going to play whatever note I tell it to play. So here's C3, right? There's C3. Metronome. So let's look at C3 through an EQ. You can see that this sine wave is registering at C4. Don't worry about it. It's a C. It's registering as a C. Here's another way of looking at that sine wave. Through an oscilloscope. And if I freeze it, yeah, you can see it is generating a sine wave for us. It's representing one. You can imagine the flat line to be nothing, and then the curve into the positive there and down into the negative. You can imagine that to be your speaker cone, just when it pushes forward and then when it kind of comes back to equilibrium, and there's kind of a rebound into the negative. So it goes, got to imagine the speaker cone going out and back in and out and in, and we are hearing the frequency of that cone in that speaker. Yeah, so the frequency, so i.e. you can look down here at something like 266 hertz. So FM8 is playing a sine wave. A sine wave, as you can see, is just its own frequency. It's just one frequency. It's whatever frequency we choose it to be at by playing in MIDI notes. So now I'm going to, as it were, turn its ability to track the MIDI keyboard by turning that ratio to 0. And now it's just going to play like whatever frequency I put in here. Let's put in 100 hertz. Okay, so you can now see this single sine wave is sort of down here. Okay, so I could double click in here, dial in 100. Let's just expand this and kind of boost the gain of that specific frequency, of course, and it will make it louder, or I can scoop it out, of course, and it seems to more or less get rid of the sound altogether. So let's think about building sounds from sine waves. We haven't said much about synthesis right now. This is obviously designed for your first lecture, Synthesis 101. This is kind of how we need to think about crafting our own sounds. Okay, it's kind of all starting with these sine waves. So here's a thought. If I turn on another oscillator, this one next door, E, and send it to the output like so, well, what happens if I put this second oscillator on the next most harmonious possible interval that we know of, which of course you all know and love to be the octave. So an octave higher than 100 hertz, I hope you can recall, is a doubling, is 200 hertz. So now we've got two sine waves playing. Notice it doesn't matter what pitch these notes are at, because it's just playing 100 hertz and then 200 hertz. So if we now look at this through this EQ, you can kind of see that two peaks have appeared. Of course, one at 100, one at 200. Okay, and I can vary the loudness of E against F. Let's just kind of make one long note just so it's slightly less irritating. We'll have a pause in there somewhere. There you go, fine. Two sine waves playing an octave apart, The first sine wave here is our fundamental. It's pushing out 100 hertz. The second oscillator here, E, is the first harmonic that we've added to the fundamental F, or it's the first overtone, and we've chosen to tell it to play 200 hertz. All right, so I'm going to keep this sort of iteration going, this sequencing going. Here's now D, is the third oscillator. Let's put D on 300 hertz. What do we get now? So hopefully you can hear that third harmonic coming in over the top. Check it out. If we look now, we can see 3 spikes at 100 hertz intervals. Let's have a quick look through this different way of viewing the sound. Again, you can see 100, 200, 300 hertz. 1, 2, 3. Great. What does it look like on the mexoscope? Well, if we get it into a reasonable domain, you can see that the sine wave is no longer a sine. It's become this slightly more complex looking creature. In a sense, you can see each of the 3 humps. You can see the fundamental and then these 2 overtones, or these 2 harmonics that we've willfully, intentionally added. Okay, what is the interval of that third harmonic? So think back to your listening skills and so on. If we take you can hopefully hear with my lovely singing that that's actually a fifth above that initial 100 hertz that we started with. So adding on that third, so we've got an octave at 200 hertz, and we have a fifth being generated at 300 hertz. You know what's coming next. Let's turn on C, 0 the ratio. What do we put it on now? I'm going to go for 400. So let's crank it up. So listen to the sound now. Check out how the mexoscope is dealing with that. It's becoming something other than a sine wave. Obviously, it's a far more complex pattern. You can now hear more going on in the sound. We've got this 4th peak, which is the loudest. If you think about it, it's actually playing another octave. Okay, so we've got 2 octaves higher now. We've got a 5th here and yet another octave. Okay, what do we have next? B. So we put B on 500. Here we go. Awesome. Now what interval, musically speaking, do you hear now? Yeah, so if you're good at your ability to discern pitch, you can hear that that's actually a major third now. So first harmonic, here's the fundamental F. The first harmonic E is playing 200 hertz, then 300, 400, 500 hertz. The 4th harmonic is sounding like this slightly flat major third. Last one is going to be, you guessed it, 600. But actually, I'm going to skip 600 because if you think about your maths, we'll be generating yet another octave. Okay, so I'm going to put it on the next one, 700, just to see what we get. So it sounds nice about here. You can hear the major third in this overall 100 hertz tone generated by B here. Major third gone, major third gone. And then we've got this really awesome, very flat indeed 7th on top. Great, so we've generated for ourselves the harmonic series. We've arbitrarily chosen 100 hertz and then added on multiples of that frequency. So not doublings. Doublings would be 200 and then 400 and then 800 and so on. And each one of those would be an octave, just every single harmonic. So that harmonic series that you can hear now, I hope in that note, you can hear that in that one note there's a 5th in there and a major third and a flat 7. And kind of craft the sound, even though it's a really boring Even though it's a really boring tone, notice how we are just crafting a slightly varying timbre from it. There's the fifth, bring the fifth back. You can hear that fifth really clearly. Okay, so how cool is that? This is, you know, the bare bones of synthesis. We start off with very simple waveforms. We add or take away harmonics, overtones, and we get different timbres. It's a really awesome thing. Okay, so I'm just going to quickly turn off all these other oscillators. We're now left with F. Let's now look at what a square wave looks like. You can see in our oscilloscope it looks like a square wave, no surprise there. And how's it going to look in a frequency analyzer? So you can see this, in some sense the same kind of thing is going on as what we had with the sine wave. We had a fundamental at 100 Hertz, and you can now see, look, that one, again I'm saying look to you, but I mean to look for you to look down here where it registers the frequency. 500 Hertz, look, 700, hopefully see that, 900, 1100. So in this square wave, rather than just stacking every single harmonic, 100, 200, 300, 400, a square wave is generated by stacking a fundamental sine wave and then every other harmonic. So if you choose 100 Hertz to begin with, the next one's at 300, the one after that's at 500. Okay, there's slightly more to the story to do with the amplitude. It's inversely related to the frequency. Okay, so if we had 300 Hertz, we would have it at 1/3 the loudness of the original fundamental. If it's at 500 Hertz, the loudness is reduced to 1/5 of the intensity. So we've got 300 Hertz at 1/3 loudness, 500 Hertz at 1/5 loudness, 700 Hertz at 1/7 of the original loudness. And if you keep iterating that into infinity, you get a squarer and squarer waveform. And so in some sense you could keep doing that sum until the end of time. You'd have this kind of infinitely square wave somehow. So I hope you're getting that. It's all good fun. Again, we could look at other preset sounds that often come with pretty much every synth on Earth. Triangle. It's got a slightly different means by which it's calculated. It's 1/n² this time. I won't say any more about that right now. This one here is a sawtooth. Sawtooths are really busy because they have every single harmonic in them. So we started off this little tutorial by, as it were, striving to make a sawtooth by just adding every single harmonic. Yeah, so I appreciate that listening to that one frequency over and over again is really dull, but again, we're kind of making this point, aren't we? So let's get that fifth back in there. Forget about that first octave, forget about that. Here's the major third, here's the flat 7. There you go, we got kind of root, fifth, major third, flat 7, kind of. Yeah, it's like a naturally occurring, 7th chord. There you go. Bring that flat 7 in a bit more. Hear that? That's a really gnarly kind of 7th. Brilliant. So how about that? We're playing, as it were, a kind of flat 7 chord, but actually we're not. We're playing one note, the fundamental note, 100 Hertz, and adding harmonics. Okay, so that's just my kind of first attempt at doing a quick explanation of the harmonic series being generated by sine waves and the beginnings of crafting sounds. Yeah.
UON Music.